Okay, let's start the last talk of the morning session, please. We have last speaker, last but not least, Victor Rivero, and he will talk about Markov additive process and the application to stable process.
Yeah, thank you very much. Thank you for the introduction. I would like to thank the organizers for giving me the opportunity to speak in this important event to celebrate the creation of this UMI. This work is based in a collaboration with Loïc Chaumont from the University of Angers in France, and Andreas Kyprian and Pait Satit Kanitkul from the University of Bath in the UK. And well, I tried to do something self-contained and accessible to a wide audience. So I will start by something that I expect is easy, random walks, and two diversifications. And that will allow me to introduce many notions that are kind of classicals. One of them is, of course, the scaling limits of random walks that leads to Brownian motion. And then I will speak about Levy processes and stable processes. That will be the first variation. And then I will speak of another variation of random walks, which is the Markov additive processes, so which is the main topic of the talk. And then I will speak about where these two diversifications meet. And they meet with a tool that is called the Lamperti transform. So I will explain that. And then I will explain how this Lamperti transform allows to study some properties of stable processes, which are classical objects in the study of in potential theory and in stochastic processes. Okay, so let's start with the simplest object, so a random walk, let's say in RD. Okay, this is usually understood as the displacement of a random walker somewhere. Okay, so we can think also of a drunk guy that is walking, and because he's drunk, he has a loss of memory property. Okay, so each time he forgets where he's coming from, and he just decides on the position he has available. Okay, so choose at n plus 1, so choose among the ones he has. Okay, so the difference of the position is the displacement of the random walker at the n step. Okay, and the probability distribution of the displacements is always the same. Okay, and all the steps are independent of the previous ones because of this property of loss of memory. Okay, well, random walks are well known. In set 2, they look like that. In set 3, they look like that. The more steps we have, the more involved the objects are. Okay, the paths of this process are. Okay. This is not a picture from yesterday night either. Okay, well, these random walks have many nice properties. They have a very robust structure, mathematical structure, and they make that makes that they have many applications in many fields, in particular in many branches of mathematics. Okay, and they are the prototype of many stochastic processes, and they allow to understand many properties of stochastic processes, as for instance the Markov property. Okay, the Markov property tells us that the future of the walker depends on the past only through the present. That's just the mathematical formalization of this idea of loss of memory. Okay, so where the walker is going at time n does not depend on how he reached its actual position, but it just depends on where he's standing. Okay, so if I'm standing next to here and I decide to walk, I will fall. Okay, or I can come back. Okay, and it will depend on where I'm standing. Okay, and there's also the homogeneity property. Okay, that means that if I just look at where I'm going from this position, it's just as if I'm seeing the random walk from any other point. Okay, as long as this is not the barrier. Okay, that is the homogeneity property. Okay, and it also has the property of independent increments. Okay, so that means that if I look at the increments of times in let's say r times the increments of the walker, Okay? Those random variables are independent random variables. Okay? And that makes also that the random walk is completely determined by the probability distribution of the increment at one step. Okay? Okay. The study of random walks is very much based in the study of the asymptotic behavior. So what happens when we make many steps? Okay, we walk long time. Okay, and well, sometimes to be able to understand that, we need to rescale the scales of time and space. Okay, so this walk, the random walk, has very few steps, but all of them are in the time scale 0, 1. Okay, so in the time interval 0, 1. Here it is the same, and here we have a lot of steps. Okay, but we rescale the time space and the space, so to be able to see everything in a whole, in a single graph. Okay, but we see something here that varies a lot. Okay, so this is what we understand as a scaling limit of a random walk. Okay, and in fact this is something that was noticed by Donsker in the 50s. Okay, he observed that if we take a random walk, a simple random walk, or a random walk with mean 0 and variance 1, okay, then he noticed that if we take the random walk in the interval 0 n scale to the interval 0, 1, okay, and a scale in a space by 1 over square root of n, when n goes to infinity, that has a limit in probability, okay, in the sense of if we observe k positions of this object, that converges to k positions of another object, and that object is what we call a Brownian motion, which is also a well-known object. Okay, Brownian motion inherits many properties from random walks. Okay, it has we can prove that it has continuous paths. Okay, but okay, in principle it can only have left limited paths and right continuous paths. But also it has the property of having stationary increments, as for the random walk. Okay, so the increment at time t plus s just depends on the length of the increment. So it's the same as observing the Brownian motion in s unities of time. Okay. Then it also has the property of independent increments. Okay, as for the random walk. So if we observe n increments, those random variables are independent. Okay, and furthermore, because this is an object that has mean 0 and variance 1, okay, so it has a distribution that is centered around the origin, okay, and in fact it follows a normal distribution. So the law of an increment is a normal random variable with variance s, okay, so it doesn't depend on t, okay, and in fact this structure that we find here gives place to something more general that is called a Levy process. A Levy process is an stochastic process that has right continuous and left limited paths, that has the property of stationary increments and independent increments. Okay, so this is not general for a Levy process. This is what is general for a Levy process. Okay, and these objects, Levy processes, are completely determined by three objects. Something that is adrift. Okay, so you have something that starts at 0. Okay, it makes some jumps and so on. So there is a drift term, a Brownian motion term, and another process, psi t, that describes the jumps. These three terms are independent, and this term is completely determined by the distribution of the jumps. Okay, the measure that describes these jumps is probably an infinite measure. That means that there are a lot of very little jumps. Okay, but normally when we draw that, we just see the big jumps because the little ones are very little. Okay, so that's the path of a Levy process, a stable process. I will tell you what it is. And in the study of Levy processes, it's very useful to study, to understand what is happening in the infimum of the process, so this green line, or the supremum of the process. This makes sense only for the dimension 1, okay? And the reason for this is that if we just observe what is happening from the infimum, so this excursion that we have here, this bit of the path has the same distribution as this bit of the path. Okay, that makes that if we collect all those excursions, we get the most simple structure that we can find in probability, that is having independent and identically distributed random variables. In some sense, because well, the random variables here are functions. Okay. But essentially, that's the simplest structure, and that allows to obtain a lot of information about Levy processes. Okay, and that makes that Levy processes in dimension 1 can be, well, can find a lot of applications, and we can derive some precise results. Not always explicit, because determining the law of this object is very difficult. Okay. But it allows to study, to make a systematic study. That is what is called the fluctuation theory of Levy processes, okay? And on which Maria Emilia worked during some time, especially in Levy processes. And she made a lot of contributions to this topic. Okay. So we have seen Levy processes so far, okay? And by the way we build a Brownian motion as a scaling limit of random walk, it can be seen that Brownian motion has a property, the scaling property. That means that a change in the scale of time is equivalent to a change in the scale of space. Okay? So that means, more precisely, that if we take a constant c and we make a dilation of the space by c, okay, and a dilation of the space by c to the minus 1/2, we obtain essentially the same object in law, okay? But we will just change the starting point, okay? It's easier to understand in this drawing, okay? So we have the path of a Brownian motion. If we zoom to this bit of the path, what we see is essentially, again, a Brownian motion, okay? So that's the property, the scaling property of a stochastic process. This scaling 1/2 may be different for other processes. Okay, so we will say that a Levy process has the scaling property if there is an index alpha, such that we have this property similar to the one of the Brownian motion. Okay, so if we make a dilation of a space by c to the minus alpha of time scale c to the minus alpha, and space by c, we obtain the same process, but just with a different starting point. Okay? And those processes, those Levy processes having the scaling property, are called stable processes. Okay? And in fact, they can be obtained by taking a Brownian motion, okay, and sampling it at random times. We cannot see it here, but here we have a process that is increasing. Okay? It has a lot of jumps, very little jumps. And it has this property of scaling. Okay? So if I sample this process at the times given by this process, I obtain something that looks like that. Okay? And it will be symmetric. And it will also have the scaling property from the Brownian motion and from this process. This is a very general way to build symmetric stable processes. Okay? Because Brownian motion also has that property of symmetry. Okay? Okay, so we cannot see much, but here's the continuation of the party. So we have Markov additive processes, and the idea is similar to the one of random walks. Okay, but now we have a very lucky guy that is drunk, and he has a lot of bottles. Okay, so when he starts his walk, before he starts his walk, he chooses one bottle, takes a sip of it, and walk. Okay? But that drink will fix a dynamic, a different dynamic. Okay? So he walks for some time, okay, and then stops, chooses another bottle, and takes another sip, and it's maybe better, so it's not doing that bad. And it waits. He doesn't remember when it was the last time he took that that last drink, okay? But eventually, at some random time, he takes another drink, okay? And he keeps walking, he keeps doing that until possibly he falls from the cliff or he finds an adulterated bottle and dies, okay? But here, in this drawing, what we see is in fact a random walk, well, a random walker that every time that he takes a sip, finishes the bottle, okay? Because we don't see a repetition of the colors, okay? So each color is a different dynamic, okay? So it's changing the dynamics, okay? And well, of course, any resemblance to reality is a pure coincidence. Okay. So we can think in something like in here. So we start with a continuous dynamic as a Levy process. So it has a drift and it jumps, drift, jumps, and so on. Okay. So after some time that is exponentially distributed, because we don't remember when was the last time we had that, when we started with this dynamic, okay, we change of dynamic. So let's say now we take a Brownian motion, okay, another exponential time passes, and now we take a different dynamic. Okay, and again we change to the other one. Okay, or we can think in something in more coordinates. Okay. So think in R3. So we have a stochastic process, and the position, the direction he will choose, or the jumps he will choose, it will depend on the direction of the particle. Okay? Well, okay, so these kind of objects have the same property of a random walk, okay? In the sense that if we observe the random walker from its actual position, the movement will look the same as the original one, okay? But starting with the dynamic that is valid at time t, okay? So if I cut and I observe the process from here, okay, what I see is essentially the same object as before, okay, but just starting with the dynamic that is fixed here, okay, that is jt. Okay, so I need to have some information about the dynamic. Okay, so that is jt. Jt is telling me from which bottle I'm drinking. Okay, so if I observe jointly the two processes, the process J and psi, I get a Markov process, a process that has the loss of memory property. Okay, and that's it. So that's a Markov additive process. Markov additive processes were introduced by Neveu in the 61, a very prominent French mathematician. And then a systematic study was carried by Schindler in the 1972. And since then, many applications have been developed, mainly in queuing theory, but we can also find applications in risk theory, financial mathematics, self-similar Markov process, as we will see in the next slide, statistical physics. And the appearance of these Markov additive processes in queuing theory is rather natural because the queues are modeled by random walks, Okay, so if we change of cashier of the people that is in the desk, we will change of random walk. Okay, so that's essentially the idea. Okay, so now let me finish with the meeting point of these two ideas. Okay, so we'll consider a Markov process or a stable process. Let's think on a stable process. So a Levy process with a scaling property as Brown in motion. Okay, so it has this property of scaling. Okay, and we'll assume the process dies at the first hitting time of 0. So if it hits 0, we kill it. Okay, and we define a new process, J and psi. J is the angle of the process, and psi is the log of the radius. Okay, but both of them are defined in the scale of time given by this functional. Okay, so this functional is running faster when x is close to 0 and slower when x is far from 0. Okay, so that makes that the path will be squeezed or enlarged when we are close or far from 0. Okay, and what Lamperti observed in the 1972 in dimension 1, and where x is only positive, is that this process, well, J is trivial, it's only 1, okay, it's a constant, and psi, what he observed is that psi is a Levy process, okay? And then later a student of Lamperti obtained a generalization of this result, but he couldn't identify the processes, and later, together with Louis Chaumont and Henry Panti, we studied the case of a one-dimensional process, so considering the sign of the process, and we obtain something that we later discover is a map. Okay, so it's a Markov additive process. Okay, and later, so recently, this result was generalized by Lilly, Chaumont, Graczyk, and Sack, and they proved that in a general space, so in RD, this process J and psi is a Markov additive process. Okay, so we have a stable process. We can transform it into a Markov additive process, and this is helpful because for Markov additive processes we have many tools as we do for Levy processes. Okay, so or at least the techniques we know to work with for Levy processes can be generalized to Markov additive process, and this opens a new gate to study or to obtain new results about the stable processes. So I will show you one result at the end of the talk, but let me just explain you what the transformation is doing. This transformation, in fact, is invertible. The inverse of the transformation is xt can be built by taking j at a time ct and the exponential of psi at ct. So j is the angle, this is the radius, okay, and ct is the first time where we cumulate enough. Where is S? U, du. So to pass above the level T. Okay, so we are running this map in the scale of time given by this function. Okay, and this is the path of the process psi. Okay, and this is the path of the process that we obtain by this transformation when J is constant. Okay, can you say where this part is coming from? This part is coming from this bit that we have here, because what this time change is doing is that we are running faster the path, the original path, when we are below 0, okay, and we are running it slower when we are above and far from 0. Okay, so this thing that we have here corresponds to this part here. Okay, so it changes the length of the path. Okay, And in dimension 1, it looks like that. So take x, keep track, take the absolute value of x, but keep track of the sign. Okay, so this is j. Okay, and then take the log of x. Continue keeping track of the sign. Okay, and do the time change. Here we don't see the time change, but what we get is the path of j and psi. Okay, so we have a colored path, as we did there. Okay, and here it also makes sense to study the supremum, the infimum. So we take for instance, the supremum here. Okay, and we should notice that this is telling us how far we are going in x. Okay, so we are not only taking the positive part, but we are taking the positive and negative part of the path of x. Okay? And that allows, again, to take excursions, as we did at the beginning, okay, and find the structures that are repetitive, that are regenerative. Okay. And as I said before, this helps in studying stable processes. Okay? And in stable processes, well, there are many variables or functionals that are interesting, okay? But none all of them are reachable, because the structure can be a bit complicated. So for instance, studying the first position or first hitting time of a ball, or the first exit time from our ball, or the position we hit, that we reach when we enter the ball, the position we hit when we exit the ball, is a problem that has attracted the attention of many mathematicians, as for instance Blumenthal, Getour, Ray, Bañuelos, among many others. Okay, but some of the tools from potential theory are limited. So with these tools, we can do we can get other kind of functionals, as for instance, the point of closest reach. What is the point of closest reach? It is known that a stable process is transient, so that means that the radius goes to infinity as t goes to infinity. Imagine we start at a point x. The process starts moving. There are many jumps. Okay. And the radius is going to plus infinity. Okay, so we want to know what is, we know that the process doesn't hit 0. Okay, so we want to know which is the point at closest distance from the origin. So this is x g infinity. And with this idea of using maps and studying the radius, because this is a function that is mainly defined in terms of the radius, okay, and the additive property of the map, the additive coordinate of the map, we were able to obtain the distribution of this random variable and observe that it has an explicit form. Okay, it looks like that. Is something that is just defined in terms of d and alpha, because we are assuming that the process is isotropic. So that means that is rotationally invariant. Okay, so if we apply a rotation to x, we get something that has the same law as the original one. Okay, and well, for dimension 1, we can obtain another functional, which is the point of furthest reach up to the first hitting time of 0. So we know that those processes in dimension 1 for alpha between 0 and 1, eventually the process hits 0. Okay, and we can obtain the distribution of this point. Okay, and that's it. So thank you very much for your attention. I enjoy the lunch.
Questions? That was after the party?
It's just now. I mean, we have 1 hour and a half.
I'd like to know if you can go the other way around. I mean, if you take an additive process or class of additive process, can you construct a Levy process or a stable process?
You can build, you can build stable processes. More general, I mean, the one we understand well in potential theory is the symmetric one or the isotropic one, and because we can have almost anything in the angle. It's very difficult to understand, but with these ideas we can build some that are easy to handle, but that will give more information about non-rotational invariant processes. So, yeah.
No, I only want to say that this was a very important improvement because for a long time we only had the transformation for positive similar Markov process, not even defined in zero.
No.
So that was from Lamperti up to about 30 or
40 years.
Only was extended to zero.
Yeah.
And then that was already a big thing, a big deal, to extend it to zero in the one-dimensional case, and then to extend it to the whole line, and then to Rn. So it's really a very important contribution that you're speaking about, because now we have a very general transformation.
Yes.
And so, I mean, when you see the difficulty you had the first extension, you can realize what it means.
There have been many works behind to reach this kind of general result that Loic obtained with his collaborators. Yeah. 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 Okay.
Let's thank the speaker.
Thank you.